Hello? Yes. Move it up a little higher. All right, thanks, Casey, and thanks, Martin, for giving a great overview of many factors of reionization. What I'm going to talk about is a model that I've been working on over the past year or two, trying to figure out whether you can reionize the universe with low escape fractions. So I'll give a little bit of a background about why we think maybe galaxy escape fractions are pretty low, and different from last talk, I will assume a set of escape fractions, and I'll show you the implications of that. So the basic thing we first need to understand is, from a galaxy standpoint, how do you actually reionize the universe? How do you calculate the contribution of galaxies to reionization? And so we can use observations to estimate that, but we have to make a few assumptions. And the first one is the UV luminosity density. And so observationally, you can observe this by measuring the UV luminosity function and taking the integral of that, and that actually tells you the UV luminosity density. But you have to assume some limiting magnitude. We think we know that galaxies don't stop simply where the Hubble Space Telescope stops seeing them. Every simulation and now some lensing work tells you it likely goes much fainter. So you have to pick a stopping point for your integral, especially when the Finkelstein slope is quite steep. That's quite important. And a common stopping point, sort of backed up by simulations, is -13. So we'll talk about that. The second one is the conversion from the UV luminosity density to the ionizing photon density. So the first quantity is the non-ionizing UV. That's the stuff we can see. We typically measure it at about 1,500 angstroms rest frame. And so we need to convert that using some assumed stellar population model, right? And so what is the ratio of 900 angstrom photons to 1,500 angstrom photons? And one of the quantities we can use to parameterize that is called Sion, which is the Lyman continuum photon production efficiency. And here's a number that we can attribute to that, which is characteristic of modestly metal poor stellar populations. And that's a commonly assumed number as well. And lastly, the product of these two tells you how many ionizing photons are made, but what we care about are the fraction that are available to actually ionize the IPM. What fraction escape the galaxy? And so this is the well-known and much maligned escape fraction of ionizing photons. And this is where I'll claim we actually have the least observational knowledge. And because of that, observers and modelers alike will assume a wide range of escape fractions, maybe 10% to maybe 50%. And so the upshot is, and I think that's one thing, so if you take these three numbers, multiply them together, that tells you how many ionizing photons are available to ionize the IgM. You can then compare that to a model or some equations for what you actually need at a given redshift and see if it works. So the upshot, and there are just a number of results there, some of mine, some of Brandt's, and some of Richard Bowen's, is that if you assume these sort of canonical assumptions, time can't be up already. Assume these typical assumptions of escape fractions of 10, 20%, limiting magnitudes of about -13, and this modestly metal poor stellar populations, reionization works with just galaxies. There's no funny business going on. So that could be the end of the story. The problem is, are these quantities actually motivated from observations? So let's talk about that. And let's start with the limiting magnitude. So over the past many decades, but really over the past 10 years, the measurements of the UV luminosity function at high redshifts, and by high redshifts, I mean roughly 4 to 10, have gotten much better. So this is a compilation I put together for a review article last year, showing observations both from space in blue, ground in green from redshift 4, where we have a lot, redshift 10, where we're really just getting the tip of the iceberg, but we can fit these pretty well with an evolving Schechter luminosity function. And so one thing I take away from this is that, especially at redshift 4 through 7, we have a really good idea of what the luminosity density is, and we have a decent guess at what it's doing at redshift 8 to 10. The problem from this is you can see the data only go down to about -17 or so. Okay? And the Feynman slope is quite steep. It's about -1.9 at redshift 6, and this fit supports a steepening slope at higher redshift. And what that means is that the luminosity density is dominated by the things we don't see. And so if we're modeling reionization, we care about where most of the photons are coming from. They're not coming from the galaxies we see with Hubble, as cool as they are. They're coming from the things we don't see. So is there any motivation for going fainter than that? Well, there are some warnings for going fainter. All right, so here is a luminosity function at redshift 7 from some candles work. And if we compare that to a simulation, sort of stretched to fit the same x-axis, these are the Croc simulations from Gannett in 2016, you can see that, yes, the luminosity functions do keep going, but then they turn over, right? And many of you in this room are familiar with this. There are physics going on here. Gas cannot cool below some limit. Once the universe is reionized, there's going to be a filtering mass that will suppress star formation. But even when the universe is neutral, there's going to be the atomic cooling limit beyond which star formation is probably very inefficient, if not zero. And so those are both encompassed into this turnover here that you see in these luminosity functions. There is evidence locally that galaxies probably did exist well below this turnover. Work by Dan Wise looking at local dwarf galaxies showing that if you take local dwarfs and sort of rewind them back to the epoch of reionization, they may have had UV magnitudes in the -5 to -10 range. But what we think, what these simulations show, and some work by Michael and Colchin is backed up, is that the luminosity function doesn't just continue steeply down to -5, it must turn over, or you overpredict the number comes locally by a lot. Okay. So what the galaxy observers typically do at high redshift is we assume it goes steeply, but then just cuts off at some point. That might not be quite physical, but when I talk about a limiting magnitude, that's what I mean. You go up to some point, and then you just cut it off. So what is that limiting magnitude, or specifically, can we rule out or confirm -13 as a valid limit observationally? And so clearly, JWST will get us closer to that limit, and I'll talk about that at the end, but we would like to do something observationally now, and this was the thinking behind the Hubble Frontier Fields program. So if you're not familiar with it, the Hubble Frontier Fields was a director's discretionary time program with the Hubble Space Telescope to obtain near UDF depth images over 6 galaxy clusters. And so you can take advantage of the gravitational lensing and see galaxies much, much fainter than you can see otherwise. And so the problem with galaxy clusters, of course, is that the clusters are bright. And so Rachel Livermore, a postdoc working with me, has spent a while trying to figure out what is the optimal way to subtract a galaxy cluster. This is our galaxy cluster subtracted image using a wavelet decomposition technique. You can read all about in her paper, and you can see there's lots of faint little blobs hiding behind the galaxy cluster. And the upshot is when we do this, now over all 6 clusters, this is a work in progress that will hopefully come out by the end of the year, you can see that the luminosity function does continue to go at a slope of about -2, with our faintest galaxy being at maybe -13, -13.5. Clearly, as you get to the fainter end, the magnification uncertainties do get higher, and that's something we're still working out right now. But broadly speaking, the data definitely rule out a turnover at brighter than -15, maybe even brighter than -14. So if we want to integrate to -13, it's probably not all that wrong. That's what I take away from it for the purposes of today's talk. All right. So that's probably okay. So we'll sort of cross that off. Still some uncertainties there, but been getting better. So what about Sion? Okay, can we assume a flat value for all galaxies at all times? And I think the answer is probably no. These are some observations of Sion from work by Bowens at redshift 4 and 5 and Dan Stark at redshift 7 or so. And this is the typically assumed value. And this bar is some work that Steve Wilkins did, just showing the range you can get from stellar population synthesis models. And what you see is that it does look like Sion is getting higher as you go to higher redshift. And that's what you might expect if metallicities are evolving towards lower values. Stars are getting hotter, they're becoming more efficient producers of ionizing photons. And so while the first assumption of a limiting magnitude of -13 I think is pretty good, an assumption of a flat Sion is probably not so good. And there is now observational evidence to back this up. So we need to keep that in mind. All right, so what could cause this? Lower stellar metallicities. Binary stars, we know that there's a big difference in the ionizing photon production efficiencies from models of binary stars versus without. Same thing with stellar rotation. More quickly rotating stars results in more ionizing photon output. So there are a lot of reasons why this can happen. And so as I mentioned before, the escape fraction is really the biggest issue. If we want to take our sort of traditional assumptions, we need an escape fraction of 10 to 20% to have reionization happen, finished by redshift 6. The data do not back that up. And so many orbits, many tens of nights on telescopes have gone to looking for escaping ionizing radiation from galaxies. And we have found it from some galaxies, but only a handful, maybe a dozen, definitely less than 20, I think. The more common result is we don't see anything. And so this is some work from Brian Sayana now 7 years ago, showing lots of bright star-forming galaxies. You don't see anything in the ionizing UV. This is some work by Eros Manzella, one of the rare examples where you actually can find something. But if you take all of the studies together, it implies that typical galaxies have very low escape fraction, probably less than 2%, with a small fraction that have a higher escape fraction. Maybe 1 out of every 20 galaxies has a higher escape fraction, something like that. All right, so clearly that is not all galaxies having an average escape fraction of 10%. And so this sort of violates our assumptions. So what do we do about this? Well, we can turn to simulations. Many simulations now are trying to predict the escape fraction from galaxies, and there are a wide range of results. But a common result is that the escape fraction is dependent on halo mass. This is a result from the first billion-year simulations from a paper by Jan-Peter Cooper, where the plot shows the probability distribution functions of escape fraction for different halo masses. So for the smallest halos, it's a pretty small box, so these are pretty small, 10 to the 7, it peaks at very high escape fraction. For the things we actually see over here, they almost always have a low escape fraction, but every now and then when a bunch of supernovae go off or something, they have a higher escape fraction. So this is maybe the origin of the 10% things we see. But on average, the escape fractions are really low. And so the question I had was, what if we take our observations of the galaxy UV luminosity function and combine it with these escape fractions? Can we actually reionize the universe? Does it actually work? All right? And so the answer is no. If you don't change anything else, this is the evolution of the ionized volume filling fraction. If you just take all the same assumptions from before, but just change the escape fractions to be those from the simulation, it doesn't work. So clearly, we need to change something else. And so this is the basic idea behind the project I've been doing, where we've been using an MCMC analysis to figure out what are the range of assumptions for these quantities that me and everybody else used to hold as fixed quantities. What are the range of assumptions that actually allow you to reionize the universe? And so this is a wonderful flow chart that if you stare at it for 10 minutes, it will maybe make sense. I'm going to skip it so I can show you the interesting results from it. But if you have questions about the process, just talk to me. All right, so how to reionize the universe with low escape fraction. Point number one. So if you use a physically motivated limit for star formation in halos, instead of assuming that galaxies form stars down to -13, look at the limiting halo masses. So before reionization in neutral regions, they should form stars down to the atomic cooling limit, which is given by this redshift-dependent line here. After reionization, galaxies in ionized regions will be photosuppressed. They won't accrete gas that depends on the virial temperature of the halos. But we don't know exactly what that is, what that halo mass limit is. There are a wide range of studies, and it ranged from maybe 10 to the 8.5 to 10 to the 10.5. And it's a little bit redshift dependent as well. And so that was one of the free parameters that we allowed. And this blue shading actually shows you the posterior on that quantity. And this shows you that the model strongly prefers forming stars and halos basically as low as you can get. There was a prior that kicked on at 8.5. So we didn't allow it to go below 8.5. That way it would never be below the atomic cooling limit. And so what this says is, if this model is correct, that the photosuppression limit is fairly low, less than 10 to the 9, maybe around 10 to the 8.5. And so if we take these halo masses and abundance match the UV luminosity functions, this is the implied limiting UV magnitude, okay? And so it evolves for a couple reasons, because the luminosity functions and halo mass functions are evolving, but also because you're going from this limit in neutral regions to this limit in ionized regions. And so this is the posterior probability of that quantity there. And you can see our fixed limit of -13 is right here. And we're never above it, and we're almost always below it, okay? So if you assume these physically motivated limiting halo masses, a limit of -13 is fine, but we actually get some extra ionizing photons out here at high redshift, maybe even a little bit at lower redshift. All right, so that's point number one. Point number two is that you need to allow galaxies to be more efficient producers of ionizing photons at higher redshifts and at fainter luminosities. So we allow Psi-ion to evolve both with redshift and with magnitude. So higher redshift galaxies are better producers, fainter galaxies are better producers. And I'm not sure if Richard's going to talk about this, but his group has some evidence that maybe both of these are the case, and clearly we'll learn a lot more with JWST. So this is showing Psi-ion versus redshift. The red line is for bright galaxies, green line is for fainter, and then blue is fainter, and purple is fainter than that. And the squares are some of the few observations we have. And so the observations were not a constraint on this. I'm just showing them that they definitely don't rule out this kind of evolution. All right. So now, based on this plot, we have a few more non-ionizing UV photons. We multiply it by this quantity, and now we're getting a lot more ionizing photons than we had before, which is good because we know the escape fractions are going to be pretty low. Okay. But as it turns out, just these two are not enough. If you just use these two, you have a really hard time finishing reionization by redshift 6. And so there's one more card up our sleeve that we can pull out, and that's a contribution from AGN. And so we allow a contribution from AGN, and we don't fix it to any particular quantity. This is the 912 angstrom emissivity as a function of redshift, and we actually allow the slope of this to vary from something like the Hopkins 2007 slope, which is pretty steep, to the interesting slope from McDowell-Hart 2015, which is motivated by the Geolongo result. And what our model actually prefers is something in between the two. It's very consistent with observations at redshift 2. The observations at higher redshift are very broad, so it's also consistent there. So AGNs contribute somewhat, and I'll show you what that means in a minute. All right. So these are the results. The blue shaded regions, again, are the posterior from our fiducial model. The green data actually shows you the constraints that were used on this model. Okay, so here are constraints on the ionized volume filling factor from McGreer et al. Here are the constraints on the ionizing emissivity from Becker and Bolton in 2013. And here are the constraints on tau, both from Planck and WMAP. We actually used the 2015 tau, which is shown by the green bar here, for our constraints. So everything works. You see a few interesting things. For example, the emissivity rises from low redshift to high to a peak, but then galaxies actually start to turn over as you have more and more galaxies in high halos, but then AGN, as shown in red, actually pick it up. And if you're worried about helium-2 reionization finishing too early, that does not appear to be the case. The red shaded region is our constraints on the helium-2 reionization redshift. It maybe starts a bit uncomfortably early, but it certainly doesn't finish. What about the escape fraction? So within this model, we can say, all right, we know how many ionizing photons were created, and we know how many actually escaped. So we can divide those two and get the population average escape fraction. And that's what's shown here. So even though the model from Parda-Cooper does not predict that the halo mass dependence of escape fraction is redshift dependent, because halo mass has changed, we actually do get a redshift evolution in the average escape fraction. And what you see is at very high redshifts, where there probably aren't all that many galaxies, it's quite high because they're in small halos, but evolves relatively steeply such that by the time redshift 4, where we can start to look for these things, you have to look at redshift less than 4, otherwise it will all be absorbed anyways. It's very low, less than 1% on average. Okay, this is showing the 68% confidence range, so it's not showing that scatter, that rare scatter that you might see. All right, and so another thing I take away from looking at this is that redshift less than 10, when reionization is basically happening, the average escape fraction is less than 5%. All right. So AGNs, are you crazy? They've already come up once in the one talk before me, so maybe I'm not so crazy. But I don't think it's crazy because they don't have to not dominate. And I think this is pretty consistent with what Martin said. If you take the galaxy emissivity and divide it by the AGN emissivity, this is what you get here. Again, the shading is a 68% confidence range, and the depth of the shading sort of shows you the shape of this posterior. So the dark line is our median there. And above redshift 5, galaxies dominate. Okay? Below redshift 4, AGN dominate. And so what I think this means is that you don't need AGNs to drive reionization at all, but you do need them sort of to push it to its end. Galaxies start to really flail at redshift less than 7. AGN really help pick up the slack and drive it to finish. All right. So is there any evidence for AGNs at very high redshift? Maybe the fluctuations in the ionizing background are some evidence. Those would be really rare quasars. I'm thinking maybe more fainter AGN or a steeper faint slope of the AGN luminosity function. But there is some evidence that have come out. A couple papers have published potential nitrogen-5 emission lines. You're only going to get nitrogen-5 from an AGN ionizing source. Okay. This is one from Tilde et al. 2015. Here's Lyman alpha at redshift 7.5. Here's nitrogen-5. This is one from Hu et al. From this year from the Logger survey. Here's Lyman alpha. Here's nitrogen-5. These two share something in common. They're not all that high significance. And so they're interesting, but far from conclusive. But again, and I'll mention this in a second, this is something we can really pinpoint with Webb, and we have much deeper spectroscopy. So what are some tests of this model in the near future? A big one is AGN, okay? So we're getting wider and wider area, larger and larger volume surveys for galaxies. What that means is we ought to be able to start to see the transition between the galaxy luminosity function and the AGN luminosity function. And we can do this now, okay? But this requires a large dynamic range in luminosity. So this is a work in progress from my graduate student, Matt Stevens at UT Austin, looking at the redshift 4 luminosity function. This is in a field called the Sheila Field, which many of you haven't heard of yet, but it's an up-and-coming field. It will be observed by the HETEC survey, which I probably won't have time to mention. I'm giving a 2-minute warning. But the upshot is we have about 20 square degrees with about 25th magnitude depth imaging. The blue points are Matt's redshift 4 luminosity function. The yellow points are my redshift 4 luminosity function from candles. And the red points are the Sloan quasar luminosity function. And what you can see is everything sort of connects. You have a galaxy luminosity function that maybe goes something like that. You have a quasar luminosity function that maybe goes something like that. And so what that means is with these data, we can actually probe the faint end of the quasar luminosity function and try and put a better measure on that. Right? He's doing that as we speak, I'm sure. Right? So look for this coming out soon, but I think this is a promising technique to maybe measure the faint end slope of the quasar luminosity function or the AGN luminosity function. And there's some interesting physics here. It does not look like, even after you subtract the quasar contribution, I don't think this is Schechter. It's going to be more like a power law. And so maybe there's interesting physics. Maybe that's just telling us something about dust attenuation in these bright galaxies. You can do the same thing with the Lyman alpha luminosity function. This is a paper by Isaac Wold, who's a postdoc at UT Austin. And this is, it's submitted, it'll be on the archive soon. This is the Lyman alpha luminosity function at redshift 0.3. And you see the same thing. Schechter, maybe some sort of galaxy contribution, transitioning to a power law that's dominated by AGN. This is a little bit more complicated because if you want to turn this into a UV faint end slope for AGN, you need to make some assumptions about the Lyman alpha equivalent width distribution in these galaxies. But it's certainly intriguing given that the, for example, hyperstar primecam surveys and the logger surveys, they've been going to wider and wider areas for Lyman alpha. And you do start to see these transitions. This is redshift 0.3, this is redshift 2, these blue points here are redshift 6.7. And so it's intriguing. And so I think there is a future there for measuring the slope of the aging luminosity function from these wide surveys. All right, I don't have time to talk about HETEX. HETEX will allow this same type of work, the phanon slope of Lyman alpha, to be done at redshift 2 to 3.5, which is maybe a slightly less exciting redshift range, but really by the end, we should be able to pinpoint it down whether the emissivity is going more like this or like this. We should find about 1 million Lyman alpha emitting galaxies with HETEX and probably a few 100,000 AGNs or so with which to do this. All right, so last slide. Implications for JWST. So how can JWST validate various aspects or rule out various aspects of this model? The first one are the faintest galaxies. So we would predict that galaxies exist down to at least -13, if not -10. All right. So if we are doing something like a UDF style program, several hundred hours per filter, you'll get down to -15 or so. It doesn't get you quite there. But if you throw a lensing cluster in the way, maybe you can get down to -11, maybe even -10. All right. So hopefully that will happen at some point. Spectroscopy with JWST will measure the evolution of the ionizing proton production efficiency. You can directly measure the psi ion quantity for galaxies and see how it depends on redshift and on magnitude. You can also, using spectroscopy, look for nitrogen 5 lines or nitrogen 4 lines or various other high ionization lines indicative of AGNs. Mid-infrared imaging with Webb will also help us get a better idea of the AGN contribution to high redshift. And lastly, escape fraction. I'm not quite sure about this. If you try to do ionized photon budgeting, so you take the observed UV luminosity from a galaxy, that tells you in principle how many stars are forming, how many ionizing photons should form. You could then compare that to a nebular line, which tells you how many are absorbed and re-emitted, and the difference is the escape fraction. That is a very interesting line of sight, but it may be dominated by systematics, but it's at the very least possible. All right, I'll take any questions.
Okay, time for questions. Yes, Richard.
Mm-hmm. Sure, absolutely. Yeah, absolutely. So one of the things on the to-do list is, I built this model originally around the Parda-Cooper model, but in the end, you can swap in any escape fraction dependence you want. And so one thing to do would be to say, what would the escape fraction have to do to rule out the AGN, which I haven't done, but certainly.
But there was a wide range of probability space for the contribution of AGN.
Yeah,
so there is some liberal time there. Yeah.
Mm-hmm. Mm-hmm. Right. Sure, yes, I'm pretty agnostic about the type of AGN that's doing this. Clearly, you would need the brightest quasars if it's going to explain the fluctuations, but it's really a non-galaxy source of ionizing photons, so it could be weak ones. Okay.
Richard, did you have a follow-up?
Mm-hmm. Well, it's actually the opposite. So the escape fraction is assumed, and a high psi ion is a result of that. Yeah. Mm-hmm. Yeah, those are individual galaxies. So, yeah. Right. Sure. Right. Yeah. Yeah, I think, so as Casey mentioned, the probability space for all of these is very broad, and that's because the constraints are low. And I didn't use constraints on Sion. When there are more robust constraints on Sion, absolutely we can use them to constrain this model. But the constraints we did use, go back really quick, this plot, the error bars are enormous, right? Here's the error bar on tau, here's the error bar on the emissivity, and the uncertainties on the volume filling fraction. And so if those were improved, or if there were additional constraints we could add, then absolutely, it could very much change this result. The steepening Feynman slope. So it's the steepening Feynman slope coupled with the evolution and ionized photon production efficiency. Not quite -10, but yeah, a little bit fainter than -13.
Maybe time for one more question. Did I see a hand? Yes.
Sure, absolutely. Right. So all that result did was get me thinking about including it as a possibility. But we are not fixed to their level of AGN, right? If you do that, as Zero showed, you don't need any galaxies at all, right? AGN can do it all. And so in this model, there are, I would say, more AGN than the classical models might assume, but not nearly as high. And that's why AGN is not being, reionization is not being driven by AGN, it's being driven by galaxies. So. Yeah.
Okay, I'm going to move the rest of the discussion to coffee. Let's thank both our speakers from this morning again. And we are a few minutes ahead of schedule, so I'm going to suggest we come back at 11:05 to allow for additional time for discussion between the next session's talks.